Right now, nearly 90% of all stars in the universe are smaller than our Sun, and yet, some stars grow so vast that our entire solar system could vanish inside them. Even more surprising, some of these gigantic stars actually weigh less than stars that look much smaller. That shouldn't be possible, but in space, size doesn't mean what you think it means. By the end of this video, you'll understand why most stars never become giants, why only a rare few grow unimaginably large, and where our Sun truly fits in the vast scale of stars. If you're ready to go deeper into this mystery, hit that subscribe button, and together, let's drift into space. We think we know what big means. A mountain, a skyscraper, an ocean that seems to go on forever. But space doesn't just stretch big into something larger. It shatters the word completely. Because out there, size isn't a feeling. It's a measurement that refuses to fit inside the human mind. And here's the uncomfortable truth. Even when we look directly at a star, even when we see it blazing like a cosmic torch, our instincts still lie to us. We guess wrong about what's large, we guess wrong about what's powerful, we guess wrong about what matters. And that's not the whole story. Because in space, the first question is never, how big is it? The first question is, what does big even mean here? Our brains were built for survival on a planet. We evolved to judge distances across a field, to estimate the size of an animal, to understand a horizon. But the universe doesn't care what our minds can handle. Space is the place where scale becomes violent. A few steps feel natural, a few miles feel manageable, a few hundred miles, a road trip. But then the numbers begin to climb and something in us fractures. Because the universe isn't built out of streets and cities, it's built out of distances so extreme that the very unit we use, a mile or a kilometre, starts to feel childish. For example, the distance from Earth to the Sun is about 93 million miles or 150 million kilometres. That sounds like a number, but it doesn't feel like a reality. So let's force it into something we can touch. If you drove a car non-stop at highway speed, about 60 miles per hour or 100 kilometers per hour, it would take you over 170 years to reach the Sun. That means if someone started driving toward the Sun during the age of Napoleon, they still wouldn't be there. And that's just one star, one distance, inside one small neighborhood of one galaxy. So when we say big in space, we're not speaking a human language anymore. Here's where the story cracks open. When we talk about big, we often mean only one thing, size. But stars don't work like that. In astronomy, big is a crowded word. It can mean radius, it can mean volume, it can mean mass, it can mean brightness. And these are not the same thing, not even close. Radius is straightforward. How far it is from the center of a star to its surface. It's the measurement we instinctively trust because we picture a ball. But then comes the trap. Because a small change in radius creates a monstrous change in volume. Volume is how much space the star actually takes up, and volume grows fast. If one star has twice the radius of another, it doesn't have twice the volume. It has about 8 times the volume. That's where our intuition collapses. Because our minds think in straight lines, the universe grows in cubes. Mass is different. Mass is the amount of matter, the amount of stuff inside the star. And stars can be deceptive. Some stars are huge in radius, but not especially massive. Others are small in radius, yet unbelievably dense, packed with matter like a cosmic fist. So big can mean wide, or it can mean heavy. And those two can point in completely different directions. Then there's brightness, what we see, what reaches our eyes. A star can look brilliant because it's truly powerful, or because it's simply close. A star can be enormous and still not appear blinding. A star can be smaller and still burn with a savage intensity. So this is the first unsettling lesson. Size alone does not define a star's power. But then, this creates a bigger problem. If radius can mislead us, if volume explodes beyond intuition, if mass hides inside the star, and brightness can lie to our eyes, then how do we measure anything at all? Picture this. Imagine we shrink the sun down to the size of a single grapefruit, about 4 inches across, small enough to hold in your hand. Now we shrink the Earth using the same scale. In that world, Earth wouldn't be a marble. It wouldn't even be a peppercorn. It would be closer to a grain of salt orbiting a grapefruit. That's the real size difference we're dealing with. Now place that grain of salt in orbit. The distance between Earth and the Sun wouldn't be across the room. It would be about 35 feet away, roughly 11 meters. Longer than most houses are wide, and even this is still only the beginning, because the nearest star beyond the Sun, Proxima Centauri, on that same scale, would not be across a neighborhood, not across a city. It would be about 36 miles away, far enough that you'd need a car just to reach the next star. And suddenly, we feel the true horror of space. Most of the universe is not filled with stars. It's filled with distance. Now we arrive at the moment where people usually get it wrong. When we hear giant star, we assume more powerful. When we hear small star, we assume weak. But stars don't reward simple thinking. A star's power, its energy output, comes from what's happening in its core. And the core doesn't care how wide the surface looks. It cares about mass. It cares about pressure. It cares about temperature. A star's size can swell dramatically during its life without gaining more matter. It can become bloated, enormous, yet not be the most massive. Meanwhile, another star can be compact, smaller in radius, but crushingly heavy for its size. So we have to separate two ideas. A star can be physically large, without being the strongest, and it can be physically small, while still holding terrifying extremes of density and force. That contradiction is the doorway into the real story of stars. But it raises another question. If we can't trust what we see, how do astronomers measure something they can't touch? Astronomers have a problem unlike almost any other science. We cannot pick up a star. We cannot weigh it directly. We cannot stretch a measuring tape across its surface. We only get light. So they built a toolkit slowly, painfully, over centuries. And each method is a way of turning light into truth. Before size can be measured, distance has to be known. Because something small and close can look like something large and far. So astronomers use methods like parallax, the same depth trick your eyes use. As Earth moves around the Sun, nearby stars shift slightly against the distant background. That tiny shift becomes a distance, and once distance is known, size becomes possible. Some stars are close enough, or large enough, that we can measure their apparent size in the sky, not as a disk we see with our eyes, but as a tiny angle. Then, using distance, astronomers convert that angle into a real physical radius. Here's the strange part. Sometimes a single telescope isn't enough. So astronomers combine multiple telescopes, sometimes across entire continents, into a coordinated system. This technique, called interferometry, lets them resolve details far beyond what one mirror could do alone. It's like turning separated instruments into one vast synthetic eye. And that's how we begin to directly measure the diameters of some stars. Sometimes the universe becomes cooperative. Two stars orbit each other in such a way that, from our point of view, one passes in front of the other. They eclipse. And when the light dips, the shape and timing of that dip can reveal the star's sizes. Not guessed, not imagined, measured. Even when we can't measure a star's disk directly, there's another path. If astronomers know how bright a star truly is, its total energy output, and they know its surface temperature, physics limits what its size can be. A hotter star of a given brightness must be smaller than a cooler star of the same brightness, because temperature changes how intensely a surface radiates energy. This isn't speculation. It's a consequence of fundamental physics that scientists use every day. So size becomes a solved problem, but only after distance, brightness, and temperature are pinned down. And still, even with all these methods, comparisons mean nothing without a reference point, because big needs context. And that leads us to the most important choice astronomers ever made. We need a baseline, a standard candle, a measuring stick, a familiar anchor inside the cosmic storm, and the sun becomes that anchor. Not because it is the biggest, not because it is the brightest, but because it is the one star we can study in brutal detail. We can measure its diameter precisely, we can map its surface, we can probe its vibrations, we can watch its storms and magnetic fields. NASA spacecraft have stared at it for decades. Observatories on Earth track it constantly. Every major model of stellar physics is tested again and again against what the sun does. So when we say a star is 2 suns wide, or 10 suns massive, or 100,000 suns bright, we are translating the universe into a language our minds can finally hold. Without the sun, every stellar comparison becomes abstract noise. With the sun, the scale becomes readable. But then, this is where everything changes, because once we accept the sun as our benchmark, we're forced to face a disturbing truth. The sun, the star that feels enormous in our sky, is not a giant, not even close. And if our own star is only the baseline, what does that say about what's waiting above it? And if you want to feel how deceptive this is, imagine you're standing outside at noon. You look up, and the sun floods the sky with light so intense it forces your eyes away. It feels dominant. It feels overwhelming. It feels like the largest thing that could possibly exist. But that sensation is not evidence of size. It's evidence of proximity. You're feeling the nearest star, not the largest one. And that single realization changes how we're going to see everything that comes next. So now we understand the trap. Big in space can mean radius, volume, mass, or brightness. Our intuition fails because the universe scales faster than our minds can follow, and even the light we see can lie. We need a stable reference. We need the star we can measure better than any other. We need the sun. But the sun is also the most dangerous benchmark, because it feels extraordinary, while being astronomically ordinary. And once we measure the sun honestly, against planets, against other stars, against what it will and will not become, we'll finally see where big truly begins. And what comes next will make our own star feel strangely small. We look at the sun and we feel certainty. It rises on schedule, it warms our skin, it lights the edges of clouds like burning paper. It feels dominant, it feels enormous. It feels like the standard of what a star is supposed to be. But this is where the universe starts to mislead us. Because the sun is not the kind of star our instincts imagine. It's not a giant, it's not a monster, it's not even close to the upper limits of what stars can become. And that's the uncomfortable twist. The star that controls our entire world is, in cosmic terms, ordinary. But then, that creates a bigger problem. If the sun feels overwhelming, yet it's only average, what does average even mean in a galaxy full of stars? Before we can understand the sun's place in the universe, we have to force its scale into human reality, because numbers alone don't land in the mind. So, let's make the sun measurable. The sun's diameter is about 864,000 miles, or 1.39 million kilometers. That's a number we can say out loud, but it still doesn't feel like anything. So here's a translation. Earth's diameter is about 7,900 miles, or 12,700 kilometers. That means you could line up roughly 109 Earths side by side across the face of the sun. 109 worlds, shoulder to shoulder, just to span that glowing disk in our sky. And volume is where it becomes almost disturbing. If we could hollow out the sun like a vast cosmic shell, We could fit roughly 1.3 million Earths inside. Not a city, not a country, not even a planet. A million worlds. And yet, even this is not what big looks like in the wider story of stars. Not even close. Imagine this. Picture a small, familiar room, your bedroom or a classroom. Now, in your mind, shrink Earth down to the size of a peppercorn, a tiny dark speck you could lose in your palm. Now, scale the sun the same way. In that room, the sun becomes a sphere about the size of a large beach ball. A beach ball next to a peppercorn. That's the relationship we live inside. But here's the part that catches in our throat. In that same scale model, the distance between the peppercorn Earth and the beach ball sun isn't across the room. It's across a space about 35 feet or around 10 meters, a long hallway. And suddenly we see the deeper truth. Even our own solar system is not mostly objects. It's mostly emptiness. And that emptiness is what makes the sun feel so powerful. Not because it is the largest star we could ever meet, but because we are close enough to burn under it. So why does the sun feel like the center of everything? Because our biology is trapped. Our eyes measure brightness as importance. Our skin measures warmth as dominance. Our lives measure time by its light. But the universe doesn't rank stars by how they feel to us. Astronomers rank stars by what they are. Their mass, their temperature, their luminosity, their lifetime. And by those measures, the sun is a main sequence star, a stable hydrogen-burning star sitting in the middle of the pack. Not the smallest, not the hottest, not the most luminous, not the most massive. Just balanced. And that balance is why it survives. But it's also why it's limited. Because stars don't get to become anything they want. Physics decides what's possible, and physics is cold. To understand the sun, we have to understand the tension inside it. A star is not calm because it is gentle. A star is calm because it is locked in a permanent struggle. On one side is gravity. Gravity is trying to crush the sun inward, unceasingly, like a slow cosmic collapse. On the other side is pressure. Not air pressure, not wind. This is the pressure of matter heated to staggering temperatures, pushing outward. And at the center of this balance is fusion. Deep in the sun's core, hydrogen nuclei are forced together under crushing heat and pressure, forming helium and releasing energy. That energy fights gravity, not as an explosion, but as a steady resistance. Astronomers call this balance hydrostatic equilibrium. But we don't need the term to feel it. We just need to understand the image. Gravity pushes in. Fusion-driven pressure pushes out. The sun exists in the knife edge between those two forces, and that knife edge holds for billions of years. But then, this raises another question. If the sun is stable, what stops it from growing into something far more extreme? What stops it from becoming one of those terrifying stellar monsters we hear about? Here's the strange part. In space, becoming bigger isn't about ambition. It's about starting conditions. It's about mass, how much material a star is born with. And the sun simply does not have enough. That single fact closes entire futures. The sun cannot become a blue giant that burns with violent intensity. It cannot become a supergiant that swallows planets in a bloated red haze. It cannot end its life as a supernova that tears space open with catastrophic force. It cannot collapse into a black hole, not because it lacks drama, because it lacks mass. Scientists at NASA and ESA model these life cycles relentlessly because the math is unforgiving. Only the most massive stars can reach the core conditions that lead to those endings. The sun's fate is different. When it runs low on core hydrogen, its structure will change, it will swell, it will brighten, it will move into a later expanded phase. But even then, it still won't become one of the universe's true giants. Eventually, it will shed its outer layers and leave behind a dense remnant, what astronomers call a white dwarf, a stellar ember, a small hot core slowly cooling in the dark. The sun is powerful enough to create life on a planet, but it is not powerful enough to die like a god. And that contrast is the point, because it forces us to admit something unsettling: the most violent stars are not the most common. We tend to picture stars as suns, bright, yellow-white, blazing, familiar. But that's a bias created by our own sky. When astronomers survey the Milky Way, they find that the most common kind of star is not like the sun at all. Most stars are smaller, cooler, dimmer. They're called red dwarfs, and they dominate the galaxy by sheer numbers. They're the quiet majority. Stars that burn slowly, live unimaginably long, and rarely announce themselves. This is why the sun is such a misleading benchmark, because it sits in a range that feels normal to us, but isn't the galaxy's default. The sun is not the typical star you'd meet if you could travel through the Milky Way. It's brighter than the average, more massive than the average, more luminous than the average. It just doesn't feel that way, because we have nothing else nearby to compare it to. And that's not the whole story, because this changes how we should interpret the night sky itself. Many of the stars we see with our naked eyes aren't the most common stars. They're the stars that are bright enough to be seen across distance. Our eyes don't show us a fair universe, they show us a biased one. And if you want to feel the deception in your bones, picture yourself standing outside at midday. You can't stare at the sun for more than a moment. Your eyes recoil. Your body flinches. It feels absolute, like the ceiling of power. But what you're feeling is not the universe's maximum. You're feeling a single star from a distance of about 93 million miles, or 150 million kilometers, close enough for its light to strike your skin with force. Now imagine that same sun placed at the distance of the nearest star. It wouldn't feel like an overwhelming god. It would look like a point, a sharp pinprick in a cold ocean of black. Brightness is intimacy, not superiority. So why do we keep using the sun as our reference? Because it is the one star we can dissect in detail. NASA spacecraft watch it continuously. Solar observatories measure its storms, its magnetic cycles, its surface motion. The sun becomes our calibration point. It's the ruler we trust because we can test it. And in that role, the sun becomes invaluable. Not because it is extreme, but because it is understood. It lets us say things like, this star is half a sun. This star is 10 suns. This star is 100,000 suns in brightness. The sun is our anchor in a universe where words like big collapse. But then, this creates the next mystery. If most stars are smaller and dimmer than our sun, what are they like? How do they live so long? How do they change the timescale of the entire universe? And why is the galaxy's most common star one we barely notice? The sun feels like the standard because it shaped our world, but it's an average star wearing the mask of a giant, only because it's close. Its balance is real, gravity pressing inward, fusion pushing outward. Its limitations are real, not enough mass to become the universe's most violent legends. And its role is real, the benchmark that lets us measure everything else. But the Milky Way is not built mostly from suns. It's built from smaller fires, dimmer, redder, quieter stars that outnumber everything we tend to imagine. And once we step into their world, we'll realize the universe doesn't belong to the brightest. It belongs to the ones that endure. When we look up at the night sky, it feels like we're seeing the universe's main cast. Bright points, sharp white fires, stars that look confident enough to be noticed. But this is where space plays its oldest trick on us, because what we see is not what's common. What we see is what's loud. And the Milky Way is not ruled by loud stars. It's ruled by a quiet majority. Stars so dim, so small, so patient, that most of them never make it into our night sky at all. They don't dominate with brilliance, they dominate with numbers, and once we understand that, the meaning of typical star collapses, because the most common star in our galaxy isn't like the Sun. It's smaller, cooler, redder, a star that burns like an ember, not a torch, a red dwarf. And that's not the whole story, because these stars don't just change what we see, they change what time means in the universe. So what is a red dwarf exactly? A red dwarf is a real star, fully alive, fully fusing hydrogen in its core, but it sits near the lower end of what a long-lived star can be. Not a planet, not a failed star, not a brown dwarf that never truly ignites sustained hydrogen fusion. A red dwarf is the smallest kind of star that can keep shining steadily for an unimaginably long time. Astronomers usually mean stars in the M class, cooler, dimmer, and far more common than the Sun. They glow more red because their surfaces are cooler than the Sun's. But here's the twist. Cooler doesn't mean harmless. It means different physics, a different pace, a different kind of endurance, and that creates a bigger problem. Because if these stars are smaller, why do they last longer? Why do they refuse to burn out the way massive stars do? We tend to imagine fuel like a pile of wood. More wood, bigger fire, less wood, smaller fire. But stars don't burn like wood. Stars burn by fusion, by forcing the smallest pieces of matter together in a core so hot and pressured that nature has no choice but to merge them, and the rate of that fusion is viciously sensitive to conditions. A massive star has a crushing core. The pressure climbs, the temperature climbs, fusion accelerates. It's not a calm flame, it's a runaway furnace. But a red dwarf doesn't have that crushing weight. Its core is still extreme, still hotter than anything we can create on Earth. But compared to massive stars, it's restrained. So fusion proceeds slowly, not because red dwarfs are weak, because they are efficient, they sip their fuel, and they do something else that feels almost unfair. Many red dwarfs churn their interiors so thoroughly that fresh hydrogen can keep circulating inward over time. So instead of burning only a central pocket of fuel, they can draw from a larger share of what they have. That one detail stretches their lifetimes into something the human mind struggles to hold. And this is where the story becomes unsettling. The universe is about 13.8 billion years old. 13.8 billion. That's enough time for continents to drift, for dinosaurs to rise and vanish, for human civilization to flicker into existence. But for many red dwarfs, that is barely the opening scene. Imagine this. Picture a candle in a quiet room. Now picture a blowtorch. Both are real flames, both are burning fuel. But one devours everything fast, hot, violent, impatient. The other can sit there for hours and steady, almost bored. That's the difference we're dealing with. Massive stars are blowtorches, red dwarfs are candles. But in space, the candle wins, because it doesn't need to impress anyone, it just needs to last. And it lasts so long that it warps our sense of the universe itself. Now, we have to confront a measurement that sounds impossible the first time we say it. Some red dwarfs are not much larger than Jupiter. Let's make that real. Jupiter's diameter is about 86,900 miles, or about 140,000 kilometers. The Sun's diameter is about 864,000 miles, or 1.39 million kilometers. So Jupiter is roughly 1/10 the Sun's diameter. Now here's the strange part. The smallest red dwarfs can have radii in the same neighborhood as Jupiter's. A star near the size of a gas giant, but it's not a planet. It's a nuclear engine. It's fusing hydrogen. It's producing light through the same fundamental process that powers the Sun. So, small becomes a dangerous word, because when we hear small, our minds imagine something fragile. But a red dwarf is not fragile. It's compact enough to be deceptive, and still powerful enough to be a star. And this creates a deeper mystery. If red dwarfs are so dim that many are invisible to the naked eye, How can they possibly be the dominant stars in our galaxy? This is one of the most important statistical truths in astronomy. Most stars in the Milky Way are red dwarfs. When astronomers count and model stellar populations, the result is consistent. Red dwarfs are the majority, often estimated around 7 out of every 10 stars in our galaxy. So why don't we feel surrounded by them? Because our eyes don't show us the average universe. They show us the loud universe. A bright star can be seen from far away. A dim star disappears unless it's close. So when we look up, the stars we see are biased toward the luminous ones. Stars that shout across distance, red dwarfs whisper, and the galaxy is filled with whispers. In fact, the nearest star system to us, Alpha Centauri, includes a red dwarf, Proxima Centauri. It's right next door in cosmic terms, and yet it's invisible to the naked eye. That's how quiet these stars are, and that's when the real problem appears. If most stars are red dwarfs, then most of the galaxy's long-term future is tied to them, and their lifetimes are so long, they force us to rethink the clock of the cosmos. Let's connect this to something we can actually feel. The sun's total lifetime on the main sequence is measured in billions of years. That's already beyond any human scale, but many red dwarfs are expected, based on stellar evolution models, to keep shining for hundreds of billions to trillions of years. Trillions! That means if a red dwarf began shining back when the first complex life was just emerging on Earth, it would still be in its early life today. If it began shining when dinosaurs first appeared, it would still be near the beginning. Even if it began shining when the pyramids were new, it would still be essentially unchanged. And if we want the truly disturbing perspective, the universe itself has not existed long enough for the smallest red dwarfs to reach the end of their normal lives. Not yet. Time has not been long enough. So we are living in a universe where the most common stars have barely started their full story, and that leads to something eerie. The night sky we see now is not the night sky the universe is designed to have. It's a young sky, a temporary sky, and the galaxy's true long-term glow belongs to stars that barely register to our eyes. When we imagine a star's death, we imagine drama, a supernova, a blinding flash, a cosmic shockwave. But red dwarfs don't die like that. They don't have the mass to reach the extreme core conditions that trigger those catastrophic endings. So instead of exploding, they fade. They change slowly, so slowly that ending is almost the wrong word. Over immense spans of time, as their fuel is used up, their output shifts. And according to the same physics models astronomers use to understand stellar life cycles, many red dwarfs should not swell into enormous red giants the way the Sun will. Their evolution is expected to be more restrained. No violent collapse, no spectacular detonation, just a long, quiet transition toward a dim remnant. So when we say many never visibly die, we're saying something precise. They don't announce their ending with a cosmic scream. They end in silence. And this is why they're haunting. Because the universe is not always a place of sudden catastrophes. Sometimes it's a place of slow inevitability. And that's not the whole story. Because red dwarfs may be quiet in brightness, but they can be intense in behavior. Astronomers have learned something unsettling about many red dwarfs. Especially when they're young, some can be magnetically active. They can flare, sudden eruptions that spike their brightness, blasting energy outward. So, the quiet majority isn't quiet in every sense. It's quiet in how far its light carries. But up close, it can be volatile. That contradiction matters because red dwarfs aren't rare corners of the galaxy. They're everywhere, and NASA missions like Kepler and TESS have shown us that planets are common around these stars. So, the most common stellar environment in the Milky Way may be a small red sun, with worlds packed close, orbiting in tight, fast years. Which raises another question. If red dwarfs are the most common stars, And if they reshape time itself, then the key to understanding stars isn't found in the giants first. It's found in the rule that governs all of them, the rule called the main sequence. And if you want to feel this personally, imagine you're standing on a rocky world orbiting a red dwarf. The star above you isn't a blazing white disk like our sun. It's dimmer, redder, like a coal that never fully turns to flame. The shadows are softer. The daylight feels muted. But you also sense something unsettling, because you're close to your star, close enough that your year is short, your sky changes quickly, and you realize the trade. This little star might shine for trillions of years, but living near it means living near its moods. Small doesn't mean safe. Small means different. So what have we uncovered? Red dwarfs are the smallest long-lived stars, true hydrogen-fusing engines near the lower edge of stellar possibility. They burn slowly because their cores are less extreme than massive stars, and their fusion rate stays restrained. Some are comparable in size to Jupiter, yet they're still stars, still nuclear furnaces. They dominate the Milky Way by sheer numbers, often around 70%, yet our eyes barely register them because they are dim, and their longevity is so vast that it changes the meaning of cosmic time. The universe is 13.8 billion years old, but for many red dwarfs that's not an ending, it's barely a beginning. And this leaves us with a final, uncomfortable implication. If we want to understand how stars truly work, not just how the brightest ones perform for our eyes, we have to understand the stage where stars spend most of their existence, the stable phase, the balancing act, the main sequence. Red dwarfs are the quiet majority. They don't dominate the galaxy with spectacle, they dominate it with endurance, but they also expose the rule behind every star we'll meet next. Mass sets the pace. Mass sets the temperature. Mass sets the lifetime. And once we step onto the main sequence, where stars spend most of their lives, we'll see this rule with terrifying clarity. Because even a small change in mass doesn't just change a star, it changes its entire fate. Out in the dark, stars look like scattered beads of light, quiet, separate, unrelated. But the universe doesn't place stars randomly. It sorts them. It judges them by a single hidden trait, and that trait decides everything: how hot they burn, how bright they shine, how long they endure. And here's the unsettling part. Most stars we will ever meet spend almost their entire lives trapped on one narrow path. A path that looks stable, but is actually a slow-motion countdown. Astronomers call it the main sequence. But that name sounds harmless. What it really is the longest balancing act in nature, and it's where the universe quietly decides what each star is allowed to become. When we say main sequence, we're not talking about a place in space, we're talking about a phase of life. A star is on the main sequence when it is doing one central thing. It is fusing hydrogen into helium in its core, steadily, for a long time. That's it. Not exploding, not swelling, not collapsing, just holding itself together. Gravity is always trying to crush the star inward, and deep inside, heat and pressure, powered by fusion, push outward. When those two forces match, the star becomes stable enough to last. This is why the main sequence is where most stars spend their lives. Not because it's dramatic, because it's efficient. But then comes the twist. Two main sequence stars can both be stable, and yet be completely different beings. One can glow red and dim like an ember. Another can blaze blue-white like a surgical flame. Same phase, same basic process, different reality. So what decides the difference? One answer: mass. We tend to think brightness is a personality. We tend to think colour is decoration. But in stars, colour and brightness are consequences. Mass is the dictator, because mass controls gravity, and gravity controls pressure, and pressure controls temperature. And temperature controls how fast fusion runs. So in a star, mass is not just how much stuff. Mass is the throttle. A star with more mass has stronger gravity. That gravity squeezes the core harder. The core gets hotter. Fusion speeds up, and the star shines more intensely, but it also burns through its fuel faster. A star with less mass can't squeeze its core as brutally. Its fusion is slower, it shines dimmer, but it lasts longer. That's the first disturbing truth of the main sequence. The universe rewards restraint with time, and it punishes excess with brilliance. But this creates a bigger problem, because our intuition expects a smooth spectrum, a little more mass, a little more brightness, a gradual change. But stars don't behave gradually. Here's where the story cracks open. On the main sequence, small changes in mass don't create small changes in outcome. They create huge differences. Because fusion is not linear, it's sensitive, it accelerates. So if a star has about twice the mass of the Sun, it doesn't become twice as bright. It can be around 10 times brighter, sometimes more, depending on the exact star. And that extra brightness isn't free. It's the sound of fuel being consumed faster. It's the sound of time being stolen from the future. Meanwhile, a star with half the Sun's mass may be far dimmer, only a small fraction of the Sun's brightness, yet it can last dramatically longer. So the main sequence isn't just a line, it's a cliff. A small step in mass can push a star into a completely different life. And once we see that, the universe starts to feel less like a gentle gradient and more like a set of strict rules. But then we have to ask the next question. If mass sets the rules, how do astronomers see those rules? How do they sort stars into this sequence in the first place? Astronomers don't begin by holding stars. They begin by reading light. They measure two things again and again: how bright a star truly is, and how hot its surface is. Put those measurements on a graph and something eerie appears. Most stars fall along a clear band, a diagonal river of points. That river is the main sequence. On one end are small, cool, dim stars. On the other end are massive, hot, luminous stars. And in the middle sits a familiar anchor, our Sun. Not at the extremes, not at the edges, near the middle, where a stable star can shine for billions of years without rushing toward catastrophe. But the main sequence isn't a category, it's a journey, and every star on it is moving, slowly, toward an ending. Imagine this. Picture a long, balanced beam like something in a gym. Every star is walking that beam. Gravity is pulling them down on one side. Fusion pressure is pushing them up on the other. A low-mass star is like a careful walker. Slow steps, small movements, a steady pace it can maintain for a very long time. A high-mass star is like a sprinter on the same beam. Fast, powerful, but burning through. Energy with every step. Both are balanced until they aren't, because the beam isn't endless. Eventually, the fuel that keeps the balance running begins to change, and that's when stability breaks. Now we can locate the Sun with new honesty. The Sun is a main sequence star. It has been stable for about 4.6 billion years. That means it began shining long before complex life existed. Back when Earth was still settling into shape, the Sun was already holding this balance, and astronomers estimate the Sun's total main sequence lifetime to be about 10 billion years. So we are roughly in the middle of its long, steady phase. There is something chilling about that, because it means the Sun is not eternal. It is stable, temporarily. And to feel what temporary means in cosmic terms, if the remaining time is roughly 5 billion years, that's 5 billion years of sunrise and sunset still ahead of us. 5 billion years is so long that when it began, Earth didn't even have land animals. When it ends, the continents will be unrecognizable. The languages we speak will be dust. But for a star, it's simply the second half of a planned life. And this is why the sun is such a powerful reference point. It shows us what balance looks like, and it shows us that balance is not forever. Here is the strange part. The main sequence is often described like a calm adult life. Steady, predictable, safe. But inside every main sequence star, the core is changing. Hydrogen is being converted into helium. Slowly, steadily, relentlessly. And helium behaves differently. It changes how the core responds. It changes how energy moves. It changes the star's structure. So even while a star appears stable from the outside, the inside is quietly transforming. The main sequence is not an endless equilibrium. It is a controlled burn. A star stays balanced only as long as its core can keep producing enough energy to resist gravity. When the core, hydrogen, runs low, the balance begins to slip. Not suddenly like an explosion, but inevitably. And this is where everything changes, because once the balance shifts, the star leaves the main sequence, and what happens next depends, again, on mass. A smaller star will drift toward a quiet ending. A larger star will move toward something more violent. So the main sequence is not just the middle of a star's life. It's the phase that decides whether the ending is silent or catastrophic. And if you want to feel the main sequence in your body, step outside on a clear day. Let sunlight hit your skin. That warmth is the outward push, energy that began in fusion deep inside the sun, then climbed outward and crossed 93 million miles, or 150 million kilometers, to reach you. Now hold the second truth at the same time. The entire sun is also trying to collapse inward under its own gravity. Every second, and it doesn't, because fusion pressure holds. You are feeling a balance that has lasted for billions of years, a balance that will not last forever. So what have we uncovered? The main sequence is where stars spend most of their lives, fusing hydrogen in their cores while gravity pushes in and pressure pushes out. Mass is the controlling variable. More mass means stronger gravity, hotter cores, faster fusion, higher brightness, and shorter lifetimes. Less mass means gentler cores, slower fusion, dimmer light, and astonishing longevity. And the most important twist: small differences in mass cause huge differences in brightness and lifetime. The universe is not gradual here. It is sensitive. It is unforgiving. The sun sits near the middle of this story, stable, bright enough to nurture a living world, but not massive enough to become the most violent kinds of stars. Which brings us to the next door we have to open, because if mass changes everything, then the stars with far more mass than the sun are not just brighter versions. They are fundamentally different machines. They burn hotter, they live faster, they dominate the light of galaxies, even while being rare. And once we meet them, we'll understand how a star can look like a jewel and still be racing toward its own destruction. The main sequence is the universe's longest performance, but it isn't mercy. It's a contract. A star trades fuel for stability, and mass decides the exchange rate. So now we're ready for the next step up. Stars whose mass forces their cores into overdrive. Stars that don't just shine, they blaze. And that blaze is not a gift, it's a warning. Because what comes next is where mass stops being a detail and becomes a countdown. When we look up at a star-filled sky, our eyes are drawn to the loudest lights, the sharp white ones, the brilliant blue ones, the stars that feel like they're trying to pierce the darkness. And our instinct is simple. If it's brighter, it must be stronger. If it's hotter, it must last longer. If it's bigger, it must be winning. But in the universe, brightness is often a symptom, a warning flare, because some of the most beautiful stars ever born are also the most rushed. They burn like cosmic blowtorches, and blowtorches don't last. Blue giants are the universe's contradiction made visible. They shine with terrifying power while racing toward an early grave. And that raises the uncomfortable question: if mass changes everything, what happens when a star is born with far more mass than the Sun? When astronomers say blue star, they're not describing a mood, they're describing temperature. Blue stars are hotter at their surfaces than yellow stars, like the Sun, and far hotter than red dwarfs. Their light shifts toward shorter wavelengths, more blue and violet, and often far more ultraviolet than our eyes can see. And giant isn't just a compliment, it's a clue. These stars are typically much more massive than the Sun. Not just a little, enough to change the physics inside them so violently that the entire pace of their lives accelerates. So a blue giant is, in many cases, a star born heavy enough to burn fast, shine brutally, and die young. But then comes the twist. Their power isn't just about size, it's about what mass does to a star's core. We can think of a star as a negotiation. Gravity pulls inward, heat and pressure push outward. On the main sequence, that negotiation holds. But add mass, and the tone changes. A more massive star has stronger gravity. That gravity squeezes its core harder. The core temperature rises, the pressure rises, and fusion doesn't simply increase, it accelerates. Fusion is not a calm dial. It's a runaway reaction that becomes more efficient, more violent, more relentless as the core gets hotter. So mass doesn't just make a star bigger, mass makes it burn differently. It turns the star into a furnace that cannot slow down. And this is why blue giants live short lives. Not because they have less fuel, they actually begin with far more fuel than the Sun. They die young because they spend it like a wildfire. And that's not the whole story, because this creates a second contradiction. Many blue giants are enormous, but their brightness still isn't explained by size alone. The real secret is luminosity. Luminosity is the total energy a star releases, not how bright it looks from Earth, how much power it is truly producing, and on the main sequence, luminosity rises brutally with mass. A star that is several times the Sun's mass can be hundreds or thousands of times more luminous. It doesn't feel fair, it doesn't feel gradual, but that's the rule the universe runs on. More mass means hotter core. Hotter core means faster fusion. Faster fusion means vastly more energy released, and energy released means light. A blue giant can pour out so much energy that from far away, it dominates the entire region of sky around it. It becomes a lighthouse in a cosmic ocean. But this creates a bigger problem. If these stars are so powerful, why aren't they everywhere? Why isn't the galaxy filled with blue giants? Imagine this. Picture two cars. One is a normal family car, steady, efficient, built to run for years. The other is a racing engine stuck at the red line. It screams, it vibrates, it pours heat, it's impressive. But you already know what happens next. It doesn't matter how much fuel is in the tank. If the engine is forced to run at maximum output constantly, it wears itself out. That's what mass does to a blue giant. It forces the core into overdrive. The star isn't choosing to burn faster. Physics is forcing it. And this is why blue giants are both magnificent and doomed. Now we can say it clearly. Blue giants are hot because their cores are extreme, and their high core temperatures affect the entire star. Energy moves outward, pressing against the star's layers. The star becomes more luminous, and often larger in radius than the Sun. But we have to be careful with the word large. Some blue stars are not the largest by radius compared to later stage swollen giants, but in their main sequence phase, they are still massive, hot, and intensely bright. They radiate with a harsh, clean light that feels almost unnatural compared to sunlight. And much of that radiation is invisible to us. Ultraviolet light that can tear electrons from atoms, transforming nearby gas into glowing clouds called ionized regions. This matters because blue giants don't just exist, They reshape their surroundings. But then, something gets stranger, because the very thing that makes blue giants so dominant, their intense radiation, also helps destroy their stability. Let's pin this to a timescale we can actually feel. The sun's life is measured in billions of years. Blue giants? Many live only millions of years. That means some of these stars can form, blaze, and die in a span of time shorter than the age of the earliest human ancestors. If a massive blue star had formed when early humans were first learning to use simple stone tools, it could already be gone. And compared to the sun's long, steady timeline, that is terrifying, because it means these stars are born in a hurry. They don't slowly mature, they erupt into existence, dominate the light of their region, and then vanish, sometimes violently. This is why they are rare, not because the universe can't make them, because they don't last long enough to stay common. But rarity doesn't mean insignificance. In fact, blue giants can dominate what a galaxy looks like. Here's the cosmic trick. What is? Common is not what is visible. Red dwarfs are everywhere, but they whisper. Blue giants are rare, but they shout. If we could map the Milky Way by number of stars, red dwarfs would dominate. But if we map by light, by what our eyes and telescopes catch at great distances, blue giants start to take over the picture. They become the bright signatures of star-forming regions. They light up nebulae. They turn cold hydrogen clouds into luminous curtains of gas. And because they burn so hot, they can be seen across vast distances. A distant region of space might contain millions of faint stars, but a handful of blue giants can still define what we notice. That's why galaxies with active star formation often look brighter and bluer. Not because blue stars are most common, because they are briefly, violently dominant, and this has consequences beyond appearance. Because when blue giants live fast, they don't leave quietly. Blue giants shape galaxies in at least 3 deep ways. These stars are born in dense clouds of gas and dust, but once they ignite, their radiation and stellar winds begin to push that gas away. They can carve cavities, they can compress nearby regions, sometimes helping trigger new waves of star formation, but they can also do the opposite, blowing away material that might have formed more stars. So, blue giants don't just appear in galaxies, they actively regulate how galaxies build new stars. The early universe was mostly hydrogen and helium. Many of the heavier elements, carbon, oxygen, silicon, iron, are forged inside stars, and the most massive stars play an outsized role in spreading those elements. When they die, they return enriched material to the interstellar medium. That material becomes the raw ingredients for later stars, planets, and eventually life. So when we talk about the chemistry of worlds, we are talking about stars that lived fast and died young. The most massive blue stars don't simply fade. Many end in core collapse supernovae, explosions so violent they can briefly outshine entire galaxies. Astronomers using observatories worldwide and space telescopes under NASA and ESA study these events because they are cosmic turning points. They create shock waves that race into surrounding space. They seed the galaxy with newly forged elements. They can leave behind neutron stars or black holes. Blue giants are not just bright stars. They are agents of galactic change. But this raises another question. If these stars burn so intensely, why doesn't their own light tear them apart while they're still alive? A blue giant is held together by gravity, but its radiation pushes outward, and the more luminous the star, the harder that radiation presses. So inside a massive star, there is a constant tension between the inward pull of gravity and the outward pressure of light. It's not just heat fighting gravity. It's the star's own brightness fighting its own stability. This is why the most massive stars are often unstable, shedding material through fierce stellar winds. They are powerful enough to erode themselves. They are bright enough to begin unraveling their own outer layers. So when we see a blue giant, we are not seeing a calm object. We are seeing a star in a state of controlled violence, held together, barely, by the force of its own gravity. And that's when the real problem appears, because if a star's mass sets its fate, then what happens when the main sequence balance finally breaks? What does a blue giant become when hydrogen in the core begins to run out? Imagine you're standing on a distant world, far enough away not to be vaporized, but close enough to see it clearly. You look up. The star above you is not warm and golden like our sun. It's sharp, blue-white, almost surgical. The daylight feels colder, not in temperature, but in emotion, like the light has no softness. And you can sense something else. This is not a star, built for patience. It is burning too hard. Even without knowing the numbers, you would feel it. This light is not meant to last. So what have we uncovered? Blue giants are the living proof that mass changes everything. They are hotter because their cores are crushed to extreme conditions. They are brighter because fusion accelerates violently under that pressure. Their luminosity rises far faster than our intuition expects. They are rare because they live fast, millions of years, not billions. And they dominate what we see because their light carries across immense distances. Most importantly, they are not just stars, they are sculptors of galaxies. They ionize gas, they drive winds, they enrich the galaxy with heavy elements, and many of them end in catastrophic collapse. Blue giants don't simply shine, they reshape the universe around them. But this is where everything changes, because a massive star cannot remain in its main sequence balance forever. When the core fuel shifts, the star's structure changes. And the next phase is one of the strangest transformations in all of astrophysics. A star can swell to a monstrous size without gaining mass. It can become cooler while becoming vastly larger. A blue giant can evolve into something that looks like the opposite of what it once was, a red giant. Blue giants show us the cost of speed. Their brilliance is not a gift, it's a countdown. And when that countdown reaches the moment core hydrogen starts to run thin, the star doesn't simply dim, it transforms, it begins to expand, and the universe performs one of its most unsettling illusions. A star can grow into a giant, not by adding anything, but by changing inside. And once we step into that swollen, aging phase, we'll see how stars can inflate beyond reason, and what that expansion does to anything unlucky enough to orbit nearby. There is a moment in a star's life when the universe performs a trick that feels impossible. The star gets bigger, not a little bigger. It swells and swells until it becomes a colossal sphere, loose and bloated, filling space where nothing existed before. But here's the disturbing part. It doesn't gain mass to do it. It doesn't add anything. It expands by changing inside. A star becomes a red giant the way a quiet object becomes a storm, not because it collects more material, but because its core stops behaving the way it used to, and that creates a bigger problem, because when a star expands, it doesn't expand alone. Anything that orbits it is suddenly trapped in a moving boundary. Worlds that once felt safe become temporary. Orbits that once felt stable become fragile. And this is where everything changes. Because our sun will do this one day, not as a theory, not as speculation, as a predicted consequence of stellar physics that NASA and ESA have modelled for decades. The sun will swell, and the inner solar system will face an ending written in heat. A red giant is not a new kind of star. It's a familiar star in a new phase of life. A red giant is what happens when a star that once fused hydrogen in its core, main sequence stability, runs low on that central fuel. And when the core fuel changes, the entire star has to reorganize itself. The core contracts, the outer layers expand, the surface cools, and the star becomes larger in radius. cooler at the surface, often far brighter overall, because the surface area becomes enormous. That combination feels contradictory. How can something become cooler and yet more powerful? How can it become bigger without gaining mass? That contradiction is the doorway. To understand the red giant transformation, we have to accept a harsh truth about stars. A star is not a flame, it's a structure. A star is an architecture built from pressure and gravity. When it runs out of hydrogen in its core, the core loses its main source of outward pressure. Gravity takes advantage immediately. The core begins to contract, and when the core contracts, it heats up. Not because it's burning more fuel, because compressing matter raises temperature, and that heat does something critical. It ignites hydrogen fusion in a shell surrounding the core. A shell, not the center. So now the star has a hot, dense core and a powerful fusion shell around it, and that shell produces a flood of energy. Energy that pushes outward into the star's outer layers. Those layers respond by expanding dramatically. The star inflates, not from added mass, from redistributed pressure. And this is the key. A red giant is not bigger because it is stronger. It's bigger because its internal structure has become unstable in a new way. It's the visible sign of an internal reorganization. And that's not the whole story, because this isn't just a distant phenomenon. This is the future of our own sun. Let's place the sun into this timeline with cold honesty. The sun has been stable for about 4.6 billion years. It is expected to remain on the main sequence for a total of around 10 billion years. So, in the far future, roughly 5 billion years from now, the sun's core hydrogen will be depleted enough that the main sequence balance begins to fail. The sun's core will contract, the hydrogen shell will ignite, the outer layers will expand, and the sun will begin swelling into a red giant. Now, we have to translate that timescale into something we can feel. 5 billion years ago. Earth was not a world of forests and animals. It was a world still transforming, its surface and atmosphere far closer to the deep past of geology than the modern planet we recognize. So when we say 5 billion years from now, we're not talking about a distant chapter in human history. We're talking about a different Earth entirely, if Earth is still recognizable at all. But even if the timescale feels unreal, the physics is relentless. The sun is not choosing its future. It is obeying a rule written into every star of its mass. And then comes the horrifying question. What happens to the solar system while the sun expands? Imagine this. Picture a small candle on a table. Now imagine the flame doesn't just burn upward. Imagine it slowly grows outward, day after day, until the flame becomes the size of the room. Not because you added wax, not because you poured fuel, but because the candle's internal structure changed, and the flame had no choice but to spread. That's what a red giant is. A star whose burning region has shifted into a shell, pushing its outer layers outward like a slow-moving tide. And in a planetary system, a tide like that has consequences. When a star expands into a red giant, its surface moves outward into space that used to belong to planets, and the inner worlds become trapped in a closing circle. For the Sun, models suggest the expanding outer atmosphere will reach into the region where Mercury and Venus orbit. Earth's fate is more complex, and scientists still debate details like mass loss, orbital expansion, and tidal interactions. But the core truth is unavoidable. The Sun's red giant phase will make the inner solar system unrecognizable. Long before the Sun physically reaches Earth's orbit, its increasing luminosity will heat Earth beyond habitability. Oceans would not survive. The surface would be transformed. Any remaining atmosphere would be driven into new chemistry, new states. So the story isn't just Will the Sun engulf Earth? The story is that Earth becomes unlivable long before any engulfing is even a question. And beyond physical engulfment, there's another effect that feels subtle but is devastating. As stars lose mass, through stellar winds during giant phases, the gravitational grip on outer planets can weaken, orbits can shift outward, systems can become rearranged. So a red giant phase is not just a bigger star, it's an era of dynamical stress, a reshaping of a star's entire neighborhood. And that creates a deeper mystery. If red giants become so huge, why are they called red, and why are they cooler? This is one of the most counterintuitive truths in stellar astronomy. Red giants can be far brighter than the Sun overall, yet their surface temperatures are lower than the Sun's, so their light shifts redder. How can a star be brighter while cooler? Because brightness isn't just temperature. Brightness is also surface area. A red giant's surface area becomes enormous, even if each square meter of its surface radiates less energy than the Sun's surface. There are so many more square meters that the total output can still rise dramatically. So a red giant becomes like a huge warm ember, not as hot as a small, fierce flame, but so vast that it dominates by sheer size. And that is why red giants can look orange or red. Their surfaces are cooler, their atmospheres are extended, their light is softer in temperature but overwhelming in volume. And here's the strange part. They can become so large that their outer layers are tenuously held, almost like a mist, a star whose edges are barely attached. So we're not just talking about a star getting bigger, we're talking about a star becoming inflated, which brings us to the physics behind stellar inflation. When the core contracts and the hydrogen-burning shell ignites, the star's energy flow changes. That energy has to go somewhere. It moves outward through the star's layers, and those layers respond. They expand, but expansion changes pressure and density. As the star expands, its outer envelope becomes less dense. It becomes more transparent in places, more convective in others. Large regions can turn into boiling, churning layers where hot material rises and cooler material sinks. The star becomes a vast, slow cauldron. And because the surface is now farther from the core, the gravity holding those outer layers becomes weaker there. So the star begins to lose material more easily. Stellar winds strengthen, the star sheds mass. This is not a minor detail. Mass loss is part of how stars like the Sun eventually end their lives. Their outer layers can be expelled into space, creating glowing shells of gas, planetary nebulae, while the core is left behind. So red giants aren't just big, they're unstable in a quiet, persistent way. They are stars preparing to let go of themselves. And that's when the real problem appears. If stars can inflate like this, how far can it go? What happens when a star starts life with much more mass than the Sun and then enters giant phases? Because for massive stars, giant is not the end of the swelling story. It's the beginning of something even more extreme. And if you want to feel what this means, imagine you are standing on Earth in that distant future. You look up, the Sun is no longer the sharp disk we know. It is larger, redder. Its light feels different, less white, more copper, more dusk. The shadows are strange. The days feel wrong, and you realize something terrifying. This isn't just a brighter sun. This is a star entering a new phase where the rules of the system are changing. The sky itself is telling you the truth. Nothing stable lasts forever. So, what have we uncovered? Red giants are a natural outcome of stellar evolution for many stars. They expand without gaining mass because the core fuel changes, the core contracts, and a hydrogen-burning shell forms, pushing the outer layers outward. The Sun will one day follow this path, swelling into a red giant roughly 5 billion years from now, reshaping the inner solar system long before any physical engulfment becomes the main issue. Planetary systems are not passive during this process. Orbits can be stressed, inner worlds can be destroyed or transformed. Mass loss can rearrange the system's dynamics, and red giants are cooler at the surface not because they are weaker, but because their energy is spread across a vastly larger surface area, turning the star into a huge, cooler-looking emitter. Red giants reveal a truth that is both beautiful and disturbing. A star can grow old by becoming larger and looser and more unstable, not by gaining strength, by changing its internal balance. Red giants are where we first watch stars break the intuition of size. A star can swell into a monstrous form, not by eating more matter, but by reorganizing its own core. But this is only the beginning, because some stars don't just become giants. They become so large that the word big collapses again. Their atmospheres become barely bound. Their size begins to flirt with instability, and they approach the edge of stellar life. The next step up is where stars truly start to break scale, supergiants. There's a point in this journey where the word big stops being useful, not because we run out of numbers, but because the numbers stop behaving like reality. Supergiants are the stars that break our mental scale. They don't just look large, they feel wrong, like the universe allowed something to inflate beyond reason, and then tried to hold it together anyway. And here's the disturbing part. Supergiants are not rare accidents. They are a predictable phase in the lives of massive stars. A phase where gravity is still winning, but only barely. A phase where the atmosphere is so loose, so extended, that the star begins to shed itself into space like fog drifting off a cliff. And once a star becomes a supergiant, it is no longer living in the long calm of the main sequence. It is living near the end. We've already met giants, stars that swell with age. But supergiants are a different category of extreme. A giant can be a star like the sun someday, expanded, older, changed inside. A supergiant is usually tied to high mass, stars born with far more material than the sun ever had. That beginning matters, because mass doesn't just decide how bright the star is. Mass decides how violently the star evolves. Supergiants are among the most luminous stars we know. They pour energy into space at rates that make the sun look quiet. And they can do it while having a surface that isn't even the hottest in the universe. Because supergiants don't dominate through temperature alone. They dominate through scale, through surface area, through sheer presence. But then this creates a bigger problem. If supergiants are stable enough to exist, how can something that huge hold itself together? To understand a supergiant, we have to stop thinking in miles and kilometers for a moment, because the size only makes sense when we compare it to the sun. Some supergiants have radii tens of times larger than the sun. Others, especially red supergiants, can be hundreds of times larger. And the biggest can reach over 1,000 suns in radius. 1,000 suns. That's not big. That's a different kind of reality. So let's translate it into something we can feel. If we placed a red supergiant with a radius about 1,000 times the sun's radius at the center of our solar system, its surface would stretch outward past the orbits of Mercury, Venus, and Earth, past Mars, and it would reach toward the region where the giant planets begin. Not a flare, not a beam of light, a star, its atmosphere, occupying that space. And what comes next challenged everything, because the bigger a star's radius becomes, the weaker gravity becomes at its surface. So, larger can also mean less held together. Imagine this. Picture a mountain covered in thick fog, not the kind of fog that sits politely, the kind that spills over the edge and slides down into the valley. Now imagine that mountain is glowing from within, not a solid object you can stand on, but a hot, luminous body losing its edges. That's a supergiant's atmosphere. It is not a clean, sharp boundary. It's extended, It's turbulent, and in places, it's barely clinging to the star at all, because supergiants don't have surfaces the way we imagine a planet does. They have layers, and those layers are constantly moving. Here's the strange part. A supergiant can be vastly more massive than the Sun, but because it is also vastly larger, its outer layers are spread thin. So the surface gravity, the grip holding the atmosphere down, can be surprisingly weak. That weakness changes everything. The outer layers can lift and fall in slow waves. Convection becomes enormous. Giant cells of rising hot gas and sinking cooler gas. The star's atmosphere becomes a restless ocean, and then radiation joins the fight. Supergiants are extremely luminous. Their light is not just illumination, it is pressure. That outward push of radiation can help drive material away, especially when dust forms in the cooler outer layers of red supergiants. So we get a star that is bright enough to push outward, and a surface gravity weak enough to let go. And that's when the real problem appeared. If a star is constantly losing mass, how long can it stay stable? Supergiants are stable in the sense that they can exist for a time without immediately tearing themselves apart. But they are not calm. They are often variable, changing brightness as their atmospheres pulse and shift. And the bigger the star becomes, the more extreme these instabilities can get. Because the star is no longer a simple main sequence engine. Inside, the core has moved beyond hydrogen. It has begun burning heavier elements in stages, and each stage changes the balance of pressure, heat flow and structure. So the outer layers respond. They expand and contract. They ripple. They shed gas. Some supergiants lose material through powerful winds that carry mass into surrounding space, creating shells and arcs of gas and dust. And those shells matter. They are the star's history written outward, evidence that this star has been unraveling for a long time. Scientists using observatories tied to NASA and ESA study these mass loss processes because they affect what happens next. Not just how the star looks, but how it dies. And that brings us to the most important truth of all. Supergiants are not a destination. They are a warning sign. A supergiant is usually a massive star in a late stage of evolution. Massive stars live fast. Compared to the Sun's billions of years, their lifetimes are measured in millions of years. So when a star becomes a supergiant, it is often already deep into a shortened life. Its core is working through fuel stages that do not last long. Each step becomes faster, more intense, more unstable, because fusion of heavier elements yields energy differently, and the star has to maintain pressure against gravity as conditions change. So the supergiant phase is not the star becoming bigger because it's thriving. It's the star becoming bigger because it's changing too fast. It's rearranging itself under pressure, and as it does, it becomes more fragile at the edges. The atmosphere loosens, the mass loss increases, the instability grows. And somewhere in that chaos is a looming consequence. When the core can no longer support itself, gravity stops negotiating. It takes over. But that's not the whole story, because supergiants don't all look the same. Some are blue-white and brutally luminous. Some are red and swollen, cooler at the surface, enormous in radius. Different appearances, same underlying truth. They are approaching an ending, and if you want to feel what supergiant really means, imagine you're standing on a world orbiting far away, far enough to survive. You look up, and the star is no longer a neat disk like our sun. It dominates the sky. It looks close even when it isn't. Its light doesn't feel like daylight. It feels like a presence pressing down on the horizon, and you realize something unsettling. A star that large doesn't just light its system, it rewrites the meaning of sky, and it also tells you, silently, that it cannot stay this way for long. So what have we uncovered? Supergiants are among the largest stable stars we know, not because the universe is careless, but because massive stars can evolve into forms where their outer layers expand to staggering radii. They differ from ordinary giants because they're tied to high mass and extreme luminosity, stars born with the kind of gravity that accelerates their entire life. They can be hundreds to over 1,000 times the Sun's radius, large enough that, in a solar system analogy, their outer atmosphere could reach past the inner planets and into the region of the giants. Their atmospheres are loosely bound because surface gravity weakens as radius increases, while intense luminosity adds outward pressure, making it easier for the star to lose mass. Instability grows with size because these stars are structurally complex, layered interiors, turbulent convection, pulsations, winds, and mass loss that can reshape the star even before its final collapse. And most importantly, supergiants are nearing the end of stellar life because they are late-stage massive stars burning through advanced phases of fusion on shortened timescales. They are not built for patience, they are built for spectacle, and spectacle is expensive. But the universe had one more twist, because even supergiants, these scale-breaking giants, are not the final edge. There are stars that look like supergiants pushed one step further. Stars so luminous that their own light fights their gravity more directly. Stars that shed mass so violently they can change in human timescales. Stars that flicker, swell, and unravel like they're barely held together. And once we meet them, we'll be forced to ask the most dangerous question in stellar physics. How large can a star become before the universe simply refuses to let it exist? That's where hypergiants begin. There are stars that feel like they belong in the normal rules of the universe. They shine, they stabilize, they endure. And then there are stars that look like they're failing in real time. Not dead, not exploding, just struggling to remain a single object. Hypergiants are what happens when a star becomes so luminous, so swollen, so violently energetic, that its own light starts to compete with the gravity trying to hold it together. They are not bigger supergiants. They are supergiants pushed to the edge, where the star is still alive, but the structure is unstable, the atmosphere is leaking, and the future is no longer calm. And this creates a bigger problem, because if a star can reach this state, then where is the limit? At what point does the universe stop allowing stars to grow? A hypergiant is not a clean, simple category like red dwarf. It's more like a warning label astronomers use when they see a star behaving in extreme ways. In plain terms, hypergiants are extremely luminous stars, often very massive, or at least born very massive, with enormous, unstable atmospheres and powerful mass loss, where the star sheds material at a staggering rate. In astronomical catalogues, they're sometimes marked as Ia+, or even zero luminosity class, meaning this is beyond a normal supergiant. They are among the most luminous individual stars we know, and scientists don't identify them because they're pretty. They identify them because their light and behavior look disturbing. Because the star is not just shining, it's unraveling. And to understand why, we have to face a force we don't usually think of as physical. Light. We grow up thinking light is gentle. It warms skin. It paints shadows. It feels intangible. But light carries momentum. And when a star becomes luminous enough, that momentum becomes pressure. Radiation pressure. Outward. Now place that against gravity, the inward force holding the star. Together, a normal star lives in a balance. Gravity pulls inward. Heat and pressure push outward. But hypergiants add a new layer of tension. Their brightness becomes so intense that the outward push of radiation can begin to lift material away from the star's surface. Not like a breeze, like a deep structural conflict. At that point, the star becomes a kind of cosmic argument. Gravity says, stay together. Light says, let go. And the star has to exist inside that argument every second. This is why hypergiants are described as barely held together. Not because they're weak, because they're too powerful, and that creates a deeper mystery. If gravity is being challenged, then how does the star respond? It does the only thing it can do. It starts shedding itself. Hypergiants lose mass through fierce stellar winds and violent episodes of ejection. They don't just leak a little gas, they can throw off entire layers. And this changes the star's life in real time, because mass is everything. Mass sets core pressure, mass sets fusion pace, mass sets fate. So when a hypergiant loses mass, it's not a cosmetic detail. It can change what the star becomes next. This is why astronomers watch certain famous hypergiants obsessively, because their surroundings aren't empty, they're wrapped in evidence. Take Eta Carinae, one of the most studied extreme stars in our galaxy. In the 1800s, it brightened dramatically in a famous outburst, ejecting huge amounts of material that now form a glowing, expanding structure sometimes called the Homunculus Nebula. Telescopes linked to NASA, like Hubble, and ground-based observatories have watched this debris cloud for decades because it's not just pretty, it's a scar, a record of a star shedding part of itself. And it tells us something terrifying. A hypergiant doesn't just age quietly, it sheds, it changes shape, it changes identity. But then it gets stranger, because this mass loss doesn't happen smoothly. It can happen in pulses, in flickers, in sudden surges, which is why hypergiants often look unstable to us, changing brightness, sometimes dramatically. Imagine this. Picture a giant balloon you're trying to keep inflated, but the balloon isn't made of rubber, it's made of hot mist, and inside it is a heater that keeps getting stronger. You pump more air in, and the balloon swells. But as it swells, the surface stretches thinner and thinner. Now the heater inside becomes so intense that it starts pushing air out through the skin, not from one hole, through the whole surface. You're not just holding a balloon, you're trying to hold together something that is actively trying to escape itself. That's a hypergiant, a star inflated to enormous size, with an atmosphere so loose that its own energy output helps drive its material away. When we say rapidly in astronomy, we have to be careful. A rapid change for a star can still be slow compared to a human lifetime. But hypergiants are special because some of their changes can be noticeable over years, decades, or centuries, timescales that feel uncomfortably close to human history. They can be variable for multiple reasons. Their atmospheres are restless. The outer layers can pulse and heave, expanding and contracting. That changes temperature, that changes brightness, that changes the star's spectrum, the fingerprint astronomers read. They can experience eruptive mass loss. Some hypergiants undergo episodes where they eject material in sudden events, not a supernova, not the final collapse, but still violent enough to reshape the star's surroundings. Dust and gas can dim them. When they eject material, that material can cool and form dust. Dust can block and scatter light, making the star appear to dim or brighten in complicated ways. So a hypergiant can look like it's flickering, not because it's turning on and off, but because we're watching a star shed layers into space, and we're seeing that debris interact with light. This is why some of these stars become legendary targets. Rho Cassiopeiae is often discussed for dramatic variability and outbursts. The Pistol star gained attention for extreme luminosity. VY Canis Majoris is studied as an enormous evolved star with heavy mass loss, surrounded by complex ejecta. These aren't characters in a story, they're real objects astronomers track, because they sit near the edge of stellar stability. And that raises another question. If hypergiants are this unstable, why don't they just expand forever? Why doesn't a star keep inflating until it fills everything around it? This is where the universe becomes brutally strict, because the same forces that allow a hypergiant to exist also set a ceiling. As a star becomes more luminous, radiation pressure rises. As the star expands, its surface gravity weakens. So with enough luminosity, the star begins to reach a point where its outer layers are no longer securely bound. Material is pushed off, winds intensify, the star loses mass faster, and that mass loss is the universe's way of enforcing limits. Even if a star begins life extremely massive, it can't keep every layer. It can't stay perfectly intact. It can't just grow and grow. It starts shedding. It starts regulating itself, violently. And beneath all of this is the harsh rule: if outward pressure becomes too strong compared to gravity, stability fails. Not necessarily in one instant, but as a trend, as a destiny, which is why hypergiants feel like they're perched on the edge of possibility. Because they are. They represent a tug of war between gravity and light, where the rope is starting to fray. And if you want to feel how unnatural this is, imagine you're looking through a telescope at a hypergiant across the galaxy. You're not just seeing a bright point, you're seeing a star surrounded by its own discarded layers, shells of gas, dust, expanding scars, and you realize you're watching a star do something that sounds impossible. You're watching it lose itself while still shining, still fusing, still alive, like a torch that keeps burning, even as the handle crumbles into ash. So what have we uncovered? Hypergiants are the edge case stars, the ones so luminous and so structurally extreme that they become unstable in ways supergiants only hint at. They're defined less by one perfect number and more by a pattern. Extraordinary luminosity, extended atmospheres, powerful winds, severe mass loss, variability and eruptive behavior that can reshape their surroundings. Radiation pressure matters here in a way it doesn't for ordinary stars. In hypergiants, light is not just what we see, it's a force pushing the star apart. Mass loss is not a side effect, it becomes the story, because losing mass changes the star's fate, and their flickering and changing is not mystical, it's physics made visible: pulsations, turbulence, dust formation, and episodic ejections. Most importantly, hypergiants reveal that the universe does not allow unlimited growth. It sets limits through stability, through radiation, through gravity, through mass loss. But then we hit the final, unavoidable question. If hypergiants are already fighting their own light, what is the exact rule that stops stars from becoming infinite? What is the hard boundary written into physics that says, no farther? Hypergiants are the edge of possibility, stars that seem too luminous to remain intact, too swollen to stay calm, too unstable to feel permanent, and yet they exist, briefly, violently, barely, which means the universe has a limit, and it enforces it. The next step is to name that limit clearly, to explain, in simple human terms, why gravity and light cannot negotiate forever, why too much mass destabilizes a star, why the universe refuses infinite growth. And once we understand that rule, we'll finally see that largest star is not just a measurement, it's a battle the universe eventually ends. We keep climbing, from dwarfs that whisper, to giants that swell, to supergiants that break our intuition, to hypergiants that look like they're unraveling while still alive. And at some point, a terrifying question becomes unavoidable. If stars can get this big, why doesn't the universe fill itself with stars the size of solar systems? Why don't we see stars that keep growing bigger and bigger until star becomes the size of an entire neighborhood of space? Because if gravity can pull matter together, why wouldn't it just keep going? Here is the problem. The universe has a limit, not a human limit, not a technological limit, a physics limit, a boundary written into the relationship between gravity and light. And once we see that boundary clearly, the idea of the biggest possible star stops being a fun comparison. It becomes a warning, because when a star pushes too hard against that boundary, the universe doesn't reward it. It destabilizes it. A star exists because two forces hold each other at the edge. Gravity pulls inward, trying to crush the star into collapse. Outward pressure pushes back, coming from heat, ultimately powered by fusion, trying to keep the star from imploding. That balance is the entire reason a star can shine for millions or billions of years. But as we move toward bigger and more luminous stars, something changes. It's no longer just heat pushing outward, it's light itself. Because in the most luminous stars, light becomes a physical force strong enough to push matter. And that creates a deeper mystery. We're used to thinking gravity is the ultimate ruler of space. But stars are places where light starts to compete. And when light competes with gravity, the universe becomes strict. Let's slow down and make this real. Gravity is a pull. It always points inward. The more mass a star has, the stronger gravity becomes, especially in the interior. To resist that, a star needs outward pressure. That outward pressure comes from hot plasma, particles moving so violently they push back. Fusion supplies the heat that keeps that motion going, but in the biggest stars, the outward force isn't just particle pressure, it's radiation pressure, pressure from photons from the star's own light. Photons don't have rest mass, but they carry momentum. When they collide with matter, especially electrons, they transfer a tiny push. One push is nothing, but a hyperluminous star produces an unimaginable flood of photons. So the pushes add up, and suddenly light is no longer just what we see. Light is something that can lift the atmosphere. That is where everything changes, because the brighter a star becomes, the more its own light begins to oppose its own gravity. And if the light becomes strong enough, it can begin to blow the star apart from the outside, not in one explosion, but by stripping it, by forcing mass loss, by refusing to let the star stay as massive as it wants to be. Astronomers have a name for this boundary: the Eddington limit. It's the point where a star's outward push from radiation is strong enough that for certain layers of the star, it can balance or overcome gravity. In simple terms, gravity is trying to keep the star's gas pulled in. Light is trying to push that gas out. The Eddington limit is where the star becomes so bright that its light can effectively levitate its outer material. And once a star is near that limit, stability becomes difficult, because the star can't keep piling on brightness without consequences. If it shines harder, it begins to drive stronger winds. It begins to eject mass. It begins to peel off its own layers. So the universe doesn't say, "You can't be brighter." It says, "If you become brighter, you won't stay intact." This is why the biggest, most luminous stars often have violent mass loss. The limit doesn't just exist on paper. It shows up as behavior, as instability, as a shedding. And this wasn't the only one, because mass itself creates another trap. The heavier a star is, the more it tries to burn fuel faster. So the very mass that helps a star become huge also accelerates the processes that tear it down. Imagine this. Picture a tug-of-war rope tied to a heavy crate. Gravity is the rope pulling the crate inward, down a slope. Now picture someone trying to push the crate uphill using a fire hose. The water doesn't just splash, it slams into the crate continuously. That fire hose is radiation pressure. In a small star, the fire hose is weak. Gravity easily wins. But in a hyperluminous star, the fire hose becomes so intense that it starts sliding the crate back upward. And once the fire hose is strong enough, you can't keep the crate stable. It jitters, it shifts, it breaks loose. That's what happens to a star's outer layers near the Eddington limit. They become hard to hold down. Now, we can say the blunt truth: stars can't grow forever, because mass creates instability from multiple directions. 1. More mass means more luminosity, and more luminosity means more radiation pressure. As mass increases, core temperatures rise, fusion accelerates, and luminosity surges. That luminosity increases radiation pressure. Radiation pressure pushes outward, so at high enough luminosity the star starts driving fierce winds and eruptions. It loses mass, which means the universe enforces a kind of self-regulation. The star tries to be massive, the star becomes too bright, the star blows off material, the star becomes less massive. It's a feedback loop. 2. More mass means faster burning, which means shorter stability. Massive stars live fast. They rush through their fuel stages. The interior becomes layered and complex. Instabilities grow. The star's structure becomes harder to maintain. Even when the star is stable in the broad sense, it can be unstable in its outer envelope, pulsating, shedding, changing. 3. The most extreme masses face deep interior instabilities. At the highest masses and temperatures, physics introduces additional instabilities that can trigger violent behavior, episodes where the star partially disrupts itself. Astronomers study these because they can change the final death pathway. We don't need to turn this into a maze of jargon. The core idea is enough. When you push mass high enough, the star stops behaving like a calm object. It behaves like a system fighting multiple failure modes at once, and that raises another question. If stars lose mass and destabilize at the high end, why don't they just keep expanding instead? Why not become enormous but diffuse, like a glowing cloud? Because fusion itself imposes limits. Fusion sounds like an engine, but it's not an engine you can throttle calmly. Fusion responds to temperature and pressure with extreme sensitivity. So if a star's core compresses, fusion can surge. That surge increases outward pressure, which can expand the star. Expansion reduces density, which can reduce fusion rate. Stars spend their lives constantly adjusting, but at extreme masses, the adjustment becomes violent. Also, crucially, fusion isn't infinitely efficient. A star can only support itself while it has the right fuel in the right place under the right conditions. Once its internal fuel stages change, the structure changes. It expands into giant phases. It sheds mass. It becomes unstable. And because massive stars evolve quickly, they reach late stages where the core can no longer produce enough outward pressure to resist gravity. And when that happens, size stops being a growth story. It becomes a prelude to collapse. So fusion provides pressure that supports size, but it also sets a timer. It is both the reason a star can exist and the reason it cannot stay in one form forever. So the universe prevents infinite growth through a combination of hard realities. At extreme luminosity, light becomes a force that drives matter outward. The star can't stay intact while becoming infinitely bright. The moment the core can no longer sustain the necessary pressure balance, gravity stops negotiating. Near the upper extremes, stars shed material through winds and eruptions, sometimes dramatically, reducing their mass and altering their evolution. A star must maintain an internal structure that can carry energy outward without triggering runaway instabilities. At the far edge, that structure becomes difficult to maintain. So when we ask, why can't stars grow forever? We're really asking, why doesn't the universe allow an endlessly stable balance at arbitrarily large mass and size? And the answer is almost poetic in its brutality, because the universe doesn't allow limitless compromise. Push gravity too hard, and you accelerate the core. Push luminosity too hard, and the star peels apart. Try to do both, and you create an object that cannot keep its own layers bound. This is why the phrase largest star is always unstable, because largest star is not a permanent category. It's a moment near a boundary, And if you want to feel this limit without equations, imagine you're holding your hand under a strong heat lamp. You can feel pressure in the form of heat, even though the light looks gentle. Now scale that up in your mind until the lamp is a star pouring out unimaginable brightness. At some point, you stop thinking of light as harmless. You start thinking of it as force. You start understanding that a star can be so luminous that its own light is no longer just a signal. It becomes a stress, a push, a threat to its own structure. That's the edge we're talking about. So what have we uncovered? Stars can't grow forever because the physics that makes stars possible also sets boundaries on how extreme they can become. Stars are held together by a balance: gravity inward, pressure outward. As mass increases, luminosity increases, and light becomes a force through radiation pressure. The Eddington limit is the simple idea that there is a brightness where light can push outward strongly enough to challenge gravity in a star's outer layers. Near that boundary, stars become unstable, drive extreme winds, and shed mass, forcing themselves back from the edge. Fusion itself creates limits because it sets the star's internal structure and timeline. As fuel stages change, the balance shifts and stability becomes temporary. So the universe doesn't allow infinite growth. It allows a brief approach to the edge, and then it demands a consequence, and this creates the final tension we can't avoid. Because if a star is pushed to the edge, massive, luminous, unstable, then the ending is not optional. The ending is built into the rules. Now we're ready for the most uncomfortable reveal of all. A star's size isn't just a measurement, it's a prophecy. Small stars fade quietly, stretched across vast time. Massive stars race toward violent collapse. So the question isn't, which stars are biggest? The real question is, what does being big do to a star's fate? Because in the next step of our journey, we'll see that death is not separate from size. Death is shaped by it, and what remains afterward, shockingly, can be smaller than the star ever was. We spend so much time chasing size. Which stars are the largest? Which ones shine the hardest? Which ones break our sense of scale? But the universe has a brutal twist waiting at the end. Sometimes the biggest stars leave behind something small. Sometimes a star that once filled a region larger than an entire planetary system collapses into an object that could fit inside a city. And the first time we hear that, it feels impossible. How can something so vast become something so compact? How can a supergiant end as a remnant smaller than Earth? Here is the uncomfortable truth. A star's death is not random. It is a signature, a final statement about the star's mass, its internal structure, and the kind of life it lived while we weren't watching. And once we understand stellar death, we realize something chilling. Size is not just appearance. Size is destiny. For stars, death is not a sudden surprise. It is the end point of a long balance. All a star's life is a negotiation, gravity pulling inward, pressure pushing outward. As long as fusion can keep generating outward pressure in the core, the star resists collapse. But fusion is not eternal, and different stars run out of fuel in very different ways. So the way a star ends is a clue. Small stars end gently because they never build the internal conditions for catastrophe. Massive stars end violently because their gravity becomes too strong for their core to support once fuel runs out. That contrast is the story of this chapter, because it shows us that the universe doesn't treat all stars the same. It treats them according to mass, and mass writes the ending. Let's start with the stars that end quietly. The smallest long-lived stars, red dwarfs, burn their fuel so slowly that they can last longer than the current age of the universe. So for many of them, death is not even something the cosmos has had time to display yet. They don't build layered cores that race through heavy fuels. They don't swell into unstable extremes. They just keep going. And when stars like the Sun reach their later stages, they also avoid the most violent endings. They expand into giants, they shed their outer layers, and the core that remains becomes a dense remnant called a white dwarf. A white dwarf is not a star still producing fusion. It's a hot, compact core cooling slowly over unimaginable time. So small and moderate mass stars do not collapse violently. They transition. They release outer layers like a slow exhale. They leave behind an ember. But that's not the whole story, because we tend to imagine the universe as dramatic, explosions, supernovas, catastrophe, yet most stars end without spectacle. The cosmos is mostly quiet endings, which raises a deeper question. Why are the loud endings so loud? Massive stars are different from the beginning. They burn fast, they live briefly, they evolve into giants and supergiants and hypergiants, and inside them the story becomes layered like an onion of fusion. As massive stars age, they can fuse heavier and heavier elements in shells. Each stage is shorter than the last. The star becomes a complex machine, stacked with burning layers. But there is a point where fusion stops being a source of support. Not because the star fails, because physics changes. At a certain stage, the core can no longer gain enough outward pressure from fusion to resist gravity. The core becomes unstable, and then gravity stops negotiating. The core collapses. In that collapse, matter is compressed to extreme states. The outer layers can rebound or be blasted outward in a supernova explosion. This is why massive stars end violently. Their gravity is too strong. Their cores become too heavy. And once the core can't support itself, collapse is inevitable. So a massive star doesn't simply run out, it falls inward, fast, catastrophically. And this is where everything changes. Because now we see that the most dramatic cosmic deaths are not accidents. They are the predictable outcomes of mass. Imagine this. Picture a massive building held up by internal pillars. Those pillars are the star's core pressure. As long as the pillars hold, the structure stands. Now imagine those pillars weaken, suddenly, because the building's internal support system shuts down. The weight doesn't slowly adjust. The weight collapses inward all at once. That's what happens when a massive star's core can no longer support itself. The star's outer layers were never floating. They were held up by the pressure of the core. When that pressure changes, gravity takes over instantly. And in the universe, gravity doesn't fall slowly. It falls hard. Now we can state the central rule clearly. A star's mass, and therefore its typical size and luminosity during life, determines how it dies. Smaller stars, quiet endings. They don't reach the extreme internal pressures needed for the most. Violent collapse. They lose mass gently and leave behind compact remnants like white dwarfs. Their death is a slow fading, not an explosion. Larger stars, violent endings. Their cores evolve through advanced stages, becoming unstable. Collapse becomes inevitable once fusion can no longer provide enough support. They can die as supernovae, leaving behind neutron stars or black holes. This is why stellar death is not a single story. It's a branching map, and that map is drawn mostly by mass. But we still haven't faced the most famous connection, supergiants and supernovae, because supergiants are not just big stars, they are stars poised at the edge of collapse. Supergiants are among the most luminous, evolved, massive stars. They often have vast, extended atmospheres. They lose mass, they can be unstable, and critically, they are late in life. When we see a supergiant, we are often seeing a star that has already burned through much of its story. The core is changing. The structure is complex. The countdown is shorter. So, when a massive star in a supergiant phase collapses, The resulting supernova can be so bright that it outshines an entire galaxy for a brief time. Astronomers track these events across the sky using global networks of telescopes and space-based observatories, because supernovae are not just fireworks. They are how galaxies evolve. They spread heavy elements. They shock nearby gas clouds. They can trigger new star formation or shut it down. And they leave behind remnants that are not just small, they are extreme, which leads to the most unsettling truth in this entire chapter. A supergiant can be enormous, hundreds to over 1,000 times the sun's radius. But the part of the star that ultimately matters in the final moment is the core. The core collapses. The outer layers are expelled or fall inward depending on conditions. What remains is the crushed core, a remnant, and that remnant can be a white dwarf for lower mass, stars, a compact object about the size of a planet, slowly cooling, a neutron star for certain massive stars, an object formed when the core compresses so intensely that protons and electrons are driven together into neutrons. Neutron stars can be incredibly small compared to the original star, closer in scale to a city than a solar system, a black hole for the most massive cores, a region where gravity becomes so intense that beyond a boundary, not even light escapes. The remnant is not a smaller star, it's a new state of matter and gravity. So the largest stars can die into remnants that are tiny in size, but monstrous in density. That's the cosmic irony. The star grows huge and then collapses into something compact beyond comprehension. It's like the universe compresses a lifetime into a final point. And that raises another question. If death reveals how a star lived, what does that say about our sun? Where does it truly stand between quiet endings and violent ones? Imagine you're watching a supergiant in the night sky. For millions of years, it has been a colossal presence, shedding mass, glowing, unstable, enormous. Then one day, the light changes, not gradually, suddenly. It becomes brighter than it should be. The star becomes a beacon, and then, in the aftermath, the giant is gone. In its place is either a tiny, spinning remnant, still screaming energy into space, or a darkness where the star used to be. You would feel it in your chest. Something that once seemed eternal just proved it was temporary. So what have we learned? A star's ending is not separate from its size. It is shaped by it. Small stars fade quietly because they never reach the internal conditions for violent collapse, and many of the smallest stars may outlive the current age of the universe. Large stars collapse violently because their cores eventually cannot support themselves against gravity once fusion can no longer provide adequate pressure. Mass determines the death pathway, quiet shedding into compact remnants or catastrophic supernova collapse into neutron stars or black holes. Supergiants are tightly connected to supernova because they are often massive stars in late evolutionary stages, approaching the final collapse. And the most unsettling truth of all, remnants are often far smaller than the original star, because the final object is the compressed core, an extreme state of matter and gravity, not a scaled-down version of the star's former size. So scale isn't just about what we see, it's about what the star becomes when gravity is no longer held back. Now we've seen the two endings, quiet, fading, violent collapse, and we've seen that big can end in something shockingly small. So where does that leave the sun? We've used it as a benchmark, but we haven't truly placed it in the full context of extremes, because after meeting dwarfs and giants and hypergiants and death itself, the sun changes. It stops feeling like the center of the story. It starts feeling like a very specific kind of star, one that sits in the middle of the universe's balance, and in the next step, we will return to the sun with new eyes, and finally understand what it means to be ordinary in a universe built on extremes. After everything we've seen, the sun should feel small. We've stood beside supergiants that swallow the idea of scale. We've watched hypergiants leak their own skin into space. We've faced the hard limits where light itself begins to fight gravity. And now we come back to the one star we live under. The sun, the star that feels so familiar. We forget how alien it really is. But here's the strange part. Once we understand extremes, the sun doesn't become less important. It becomes more terrifyingly precise, because the sun sits at a narrow, stable middle, where the universe is quiet enough for time to matter. And that raises a question that's almost uncomfortable. What if ordinary is the rarest miracle of all? When we look at the sun from Earth, it dominates everything. It paints our skies. It sets our clocks. It rules our biology. So our instincts call it gigantic. And in human terms, it is. The sun's diameter is about 1.4 million kilometers, or about 865,000 miles. Earth's diameter is about 12,700 kilometers, or about 7,900 miles. So if Earth were the size of a small bead, the sun would be a sphere you could hold with two hands. Still smooth, still glowing, still unimaginably dangerous. By volume, you could fit about 1.3 million Earths inside the sun. 1.3 million. That number should feel ridiculous. And yet, compared to the largest stars we've met, the sun is not the titan. It's the baseline. A stable, middle-class star. A star that shines without tearing itself apart. A star that doesn't rush. And that is not weakness. That is design, written by physics. We used the sun as our measuring stick because we had to. But now we can finally see what the sun actually is. A main sequence star in a long, balanced phase, burning hydrogen in its core. Not the smallest, not the largest, not the hottest, not the brightest, but stable, predictable, the kind of star that can keep a planetary system illuminated for billions of years. And when we say billions, we need to feel what that means. The sun is about 4.6 billion years old. When it formed, Earth itself was still becoming a world, long before complex life, long before dinosaurs, long before the first humans. The sun has been steady through ages that swallow civilizations like dust, and that steadiness is the real power. Because in the universe, the most important resource is not light, it's time. We tend to fall in love with extremes, the brightest supernovae, the biggest supergiants, the most violent collapses. But the universe doesn't run on its most dramatic stars. It runs on its ordinary ones, because massive stars live fast and die young. They can blaze with thousands to millions of times the sun's luminosity, but only for a brief cosmic moment. They are like matches in a storm, bright, violent, and gone. Meanwhile, stars like the sun keep shining, not for millions of years, for billions. That long stability does something the universe desperately needs. It creates steady environments. It allows planets to cool, oceans to form, atmospheres to evolve, chemistry to build complexity without being reset by constant catastrophe. This is why it matters. The universe isn't just a place of explosions, it's also a place of slow assembly. And without stable stars, assembly becomes almost impossible. But then this creates a bigger problem, because stable stars are not the only kind. In fact, the most common stars are smaller than the sun. So why does our story, our existence, happen to orbit a star like this? What makes this middle ground so special? Stability doesn't mean safety. Even our sun can produce storms, flares, eruptions. But over long timescales, the sun is remarkably consistent for a star. It doesn't flood the solar system with constant lethal radiation. It doesn't change brightness so dramatically that planets freeze and boil in rapid cycles. It gives planets a chance to become more than rocks. And on Earth, that chance took time. Life didn't appear as a finished product. It climbed, slowly, through deep time, from simple cells to complex organisms, through extinctions and recoveries, through long experiments written in DNA. That process is fragile. It requires a stable energy source across unimaginable spans. So when we say stars enable life, we're not making a romantic statement. We're stating a physical requirement. Complexity needs time without constant reset. And in our galaxy, the stars that offer that kind of time are mostly the small ones. Red dwarfs are the quiet majority, but stars like the Sun offer a different kind of stability, one that includes a wide habitable zone and a long, calm main sequence lifetime. And here's where the story cracks open. The Sun's size, its mass, places it in a rare balance between longevity and energy output. Not too dim, not too violent, not too short-lived, just enough. Imagine this. Picture a campfire in the dark. If it burns too weakly, the cold wins. If it burns too violently, it throws sparks everywhere and collapses into ash. Now imagine you're not camping for one night. Imagine you're trying to build a city around that fire. You need it steady. You need it predictable. You need it to burn long enough for roads, homes, and generations to exist. That's what the Sun is to our solar system. Not just a light, a long-duration flame, a stable center that makes long-term complexity possible. And when we compare it to massive stars, we see why that matters. A blue giant might blaze with terrifying brilliance, but it doesn't give its planets billions of years. It gives them a short, intense window, and then it collapses. We often confuse bigger with better, but in stars, bigger often means hotter cores, faster fusion, shorter lifetimes, stronger winds, more instability, and a more violent death. So the Sun's size is not a weakness. It's a trade. The Sun is massive enough to shine brightly in warm worlds, but not so massive that it races toward collapse in a few million years. It is strong enough to be reliable, and reliability is rare in a universe built on change. This is why astronomers care so deeply about the Sun's classification and behavior, because it represents a stable template, one that can guide our understanding of other planetary systems. It's also why institutions like NASA and ESA invest so much into solar observation. Not because the Sun is mysterious in the dramatic way a black hole is, but because the Sun is a quiet engine that makes everything else possible for us. And once we see that, the question shifts. Instead of asking, how big can stars get? We start asking something heavier. What would the universe look like if stability was uncommon? We have to be careful here, because we're not inventing fiction. We're following physics to its logical consequences. Massive stars live fast. They pour out intense ultraviolet radiation. They push powerful winds into their surroundings. They explode as supernovae, enriching space with heavy elements, but also flooding regions with shock waves and energetic particles. So if a universe, or even a galaxy, were dominated by giant stars, the environment would be harsher and more rapidly changing. Not because the universe would choose violence, but because high mass demands high luminosity, and high luminosity accelerates everything. Star formation would be shaped by powerful feedback. Gas clouds would be disrupted more often. Planetary atmospheres would face stronger radiation pressures, and many planetary systems would have less time to settle into long-term stability before their star's life ended violently. The result wouldn't be no planets. Physics allows planets to form in many conditions, but the window for calm, long-term evolution would shrink, and that matters because life, especially complex life, doesn't just need energy. It needs time without constant catastrophe. So in a giant-dominated cosmos, the universe might glow brighter, but it would burn faster. It would be more spectacular and less forgiving. Which brings us back to our star, with new respect. The Sun is not small in human terms, but in cosmic terms, it is a deliberate middle. a star that doesn't dominate through violence, a star that dominates through patience. And if you want to feel what that means, step outside at noon in your mind. Feel the sun on your skin. Not the poetry, just the raw reality. That warmth is the result of a nuclear furnace 150 million kilometers away, about 93 million miles, stable enough that you can build your entire life around it without it changing its mind tomorrow. You can plant crops, you can make calendars, you can plan for decades. In the universe, that kind of predictable light is not guaranteed. It's earned by a star sitting in a narrow balance. So where does the sun truly stand? After understanding extremes, we see the sun not as average in a dismissive way, but as essential in a structural way. It is a stable main sequence star in a long-lasting phase. Its size and mass place it in a balance, luminous enough to support warm planets, long-lived enough to allow billions of years of planetary and biological evolution. Ordinary stars are the backbone of the universe because they provide time for galaxies to mature and for complex systems to assemble. The sun's size is not a weakness, because in stellar physics, extreme mass often trades stability for spectacle. A universe dominated by giants would be more intense and more rapidly changing, with shorter-lived stars and more frequent violent endings shaping the environment. So the sun is not the biggest. It is not the brightest. But it might be one of the most important kinds of stars there is, because it makes long stories possible. And once we accept that, we arrive at the quietest truth of all. The universe does not reward extremes. It rewards balance. We began this journey chasing size, but size alone never told us what mattered, because a star can be enormous and brief, or modest and enduring. And now, standing beneath our sun with this new perspective, we feel the silence behind the numbers, the cosmic reality that most stars are smaller than the sun and will outlive it, the reality that giants burn bright and vanish, and the reality that we exist in the narrow corridor where a star can be stable long enough for meaning to accumulate. So as we step into the final moment of this series, the question changes again. Not which stars are biggest, but what does scale mean when we measure it against time, against survival, and against us? Because the universe is not just vast, it is vast and quiet and patient, and we are a brief flicker inside that patience. Out there, the universe is full of monsters, stars so large they could swallow the space where worlds should be, stars so bright they can bleach the dark from entire regions of a galaxy. And yet, most of the universe does not scream. Most of it sits in silence, because size is not the final truth. A supergiant can burn like a cosmic alarm and vanish in what amounts to a blink. A small star can whisper and keep whispering long after entire civilizations rise and disappear. So the question we started with, how big can stars get, was never the real question. The real question is harder. What does big even mean, when time is the real currency of the cosmos? And what does it mean for us, living under one ordinary star, to realize the universe is built not on spectacle, but on balance? Every star we've met, dwarf, giant, supergiant, lives inside the same cage. Gravity pulls inward, pressure pushes outward. That's the whole struggle. Albert Einstein taught us that gravity isn't just a force, it's the shape of reality itself. Stephen Hawking spent his life warning us that when gravity wins completely, even light can be trapped, and stars live on that knife edge. A star is not just a glowing ball, it's a negotiation, a constant argument between collapse and resistance. Fusion in the core pushes outward, gravity demands the star fall inward, and for a while, sometimes for billions of years, something miraculous happens. The argument reaches a balance, but then The fuel changes, the core changes, the pressure changes, and the universe reveals what the star truly was all along. Because every ending we've seen was written in the beginning, not by fate, by mass, by physics, by the same laws that shape everything we touch. We are built to respect large things, a mountain, a storm, an ocean. Our brains learned survival by measuring threats in human scale. But space doesn't care about our instincts. In space, big is not a feeling, it's a measurement. And even then, it's complicated. A star can have a huge radius and still be loosely held together, its outer layers barely clinging to it. A star can be smaller in radius but far more massive, dense enough to bend the behavior of matter itself. Brightness can fool us too. Some stars look powerful because they're hot and luminous, not because they're physically enormous. Some stars look dim because they're small and cool, even if they will outlive everything else around them. So if we judge stars the way we judge everything on Earth, by what looks biggest, by what looks loudest, we misunderstand the universe immediately. And this is where everything changes, because the universe does not reward the loudest stars. It uses them, and then it moves on. Here is the uncomfortable truth. The most spectacular stars are not the most important stars. They're rare, they're brief, they are fireworks. Yes, massive stars shape galaxies, they forge heavy elements, they explode as supernovae and scatter the raw materials for planets and bodies and oceans. But they do not sustain the universe. They don't give time, they don't give stability, they don't provide the long, steady light that allows complexity to assemble slowly. Meanwhile, smaller stars, quiet stars, do the patient work. They burn for so long that the universe itself has not yet lived long enough to watch many of them fully die. And that means importance is not about domination. It's about endurance. It's about what remains. It's about what keeps going when the show ends. We've seen why extremes break. The biggest stars fight their own light. Radiation pressure pushes outward so hard it can tear matter away. Winds strip mass. Instability builds. At the high end, the universe sets boundaries, not as a preference, but as a consequence. Too much mass leads to violent lives and violent deaths. Too much luminosity creates its own problem. The star can begin to blow itself apart. At the low end, stars can't be too small either, because below a certain threshold, gravity can't squeeze the core hot enough to sustain fusion. So there is a corridor, a range where stars can be stable, and in that corridor, something quiet happens. The universe becomes predictable enough for long stories. Not dramatic stories, long stories. This is why it matters. Because long stories are where planets form, where atmospheres settle, where chemistry has time to experiment. The cosmos isn't built around constant catastrophe. It's built around long, steady balances, punctuated by moments of violence. And we live in the aftermath of both. We've seen it again and again. Big stars burn fast. They live like cosmic tragedies. They blaze, staggeringly bright, then collapse. Smaller stars do the opposite. They sip fuel. They stretch time. If a massive star is a bonfire that roars through the night, a small star is a candle that refuses to go out. And that changes how we should see the sky. Because the stars that dominate our eyes are not the stars that dominate the galaxy. The bright, blue, rare giants steal attention. But the quiet majority, cooler, smaller stars, make up the bulk of the stellar population. The universe is not mostly made of giants. It is mostly made of persistence. So when we talk about the scale of stars, we're not just ranking sizes. We're witnessing two different philosophies of nature. Power that burns quickly, power that lasts, and the universe chooses the second far more often. Imagine this. Picture a sleeping city at night. Most homes are dark, Most streets are quiet, but somewhere a siren cuts through everything. An ambulance, a police car, a bright moving flare of noise and light. That's what a massive, luminous star is in a galaxy. It grabs our attention because it's intense, but the city isn't made of sirens, it's made of quiet rooms. It's made of steady lights behind windows. It's made of ordinary life, continuing. In the same way, the galaxy isn't made of its brightest stars. It's made of the countless quiet ones we don't notice first. The universe looks dramatic from far away, because our eyes are drawn to the sirens, but the universe runs on the quiet rooms. Even the distances between stars carry this same lesson. The nearest star system is so far that light, moving faster than anything we know, still takes years to reach us. And if we try to translate that into human movement, it becomes humiliating. A passenger jet can cross a continent in hours, but at that speed, the trip to the nearest star would take longer than recorded human history, longer than empires, longer than languages. And that emptiness between stars isn't just empty space. It's a reminder. The universe is not a stage built for our instincts. It is built for physics. So our job is not to feel the cosmos correctly. Our job is to understand it, slowly, carefully, with humility. Now we can say something true without exaggeration. We are here because of extremes and because of balance. The heavy elements in our bodies, iron in our blood, calcium in our bones, come from stellar interiors. Many were spread through space by stellar deaths. The violent endings matter. They seed galaxies. But the calm, balanced stars matter too. Because once those elements exist, they need time to gather into worlds, time to become oceans, time to become biology, time to become memory. We are not the children of one kind of star. We are the result of a whole system, short, violent lives that forge and scatter, and long, stable lives that illuminate and sustain. And when we realize that, the story becomes deeply human, because we are the same. We are brief, but we are built from things that lasted. We are small, but we are made by processes that operate on unimaginable scales. And we live under a star that is neither the smallest nor the largest, but stable enough to let meaning accumulate. Tonight, if you step outside, just for a moment, and look up, you might see only a handful of stars. But you're not looking at a handful of objects. You're looking at a river of distance. You're looking at light that left long before you made that decision. Some of that light began its trip before the first cities, before the first books, before the first names, and you're standing there, breathing, under a sky that does not care about your scale. Yet somehow, your mind can reach it. Your mind can understand the difference between radius and mass, between brightness and power, between a quiet star that endures and a giant star that collapses. That is the quiet connection. Not that we are big, but that we can see bigness clearly. So here is what this journey leaves us with. Stars vary wildly in size, temperature, brightness, and lifespan, but they all obey the same laws. Size does not equal importance. The universe favors balance over extremes because extremes destabilize themselves, while stability can persist for billions of years. Smaller stars, though less dramatic, often outlive giants by staggering margins, quietly shaping the long future of galaxies. And our place in this story is not accidental in meaning, even if it is accidental in history. We live under a star that gives time, a star whose ordinary steadiness is not weakness. It is the condition that allows long stories, like ours, to exist at all. We came here chasing the true scale of stars, but the final scale is not just kilometers or miles, it's time, it's endurance. It's the difference between a brief blaze and a long, steady glow. The cosmos is full of giants, but it is built by what survives. And in the silence between those distant fires, we find something almost unsettling. The universe doesn't need to be loud to be powerful. It only needs to keep going, and so do we. Because in the end, we are not measuring stars to feel small. We are measuring them to understand the reality we inhabit, a reality where even the most monstrous light must obey gravity, where even the biggest star must eventually surrender, and where, for a brief moment, under one ordinary sun, we are allowed to witness it.